Okay, so we've started talking about velocity. We started talking about acceleration. So first and foremost, tell me our equation for velocity. V equals displacement over time, delta x over delta t. Okay, and then we moved on to acceleration, which, what does an acceleration mean? What's it mean to have acceleration? It means we have a change in velocity, right? Very good. We have a change in velocity. So that means the equation for simple acceleration is, delta v over delta t, right? Acceleration equals change in velocity over change in time. So velocity tells us the rate at which our position changes. Acceleration tells us the rate at which our velocity changes. Okay, so we're going to deal now with things that have constant acceleration or uniform acceleration. Okay? We're going to use this set of 4 kinematic equations. Okay, our kinematic equations for constant acceleration. But you'll commonly hear me refer to these equations as your kinematic equations. And there's a set of 4 of them. 3 which are used a lot. The last one is not used very much at all. But I'm going to give you all 4 so you have them. Okay, so these are our kinematic equations for constant acceleration. These equations are not valid if we have varied acceleration. We've got to have constant acceleration. Okay, these equations will not work if we have non-uniform or non-constant acceleration. Okay? And every problem that we do that requires our kinematic equations will have uniform acceleration. That kind of goes without saying, but you do need to be careful that it doesn't say anywhere in your problem that you have non-constant acceleration. Okay, so here's our first equation here. V equals V sub O plus AT. Okay, so we mentioned just briefly what these subscripts kind of mean and what our variables mean, but we're going to walk through each of them one by one so that we have a very, very good understanding of what they are. So V by itself is final velocity. And what's our units for velocity? Yeah, meters per second, good. Okay. V sub 0. Does anyone know what that means? Initial velocity, okay? And your book represents it with a 0 because it's saying that at time 0, okay, or at the beginning of our problem, this is the velocity. So this is initial velocity. Okay, that's also in meters per second. What about A? What do you think A means, little a? It's acceleration, good. And our units for acceleration are? Good, meters per second squared. Now, it's important to understand that when we talk about constant acceleration, we don't mean that every single problem we do will have the same value, the same magnitude of acceleration. We mean that in that problem, in that particular motion or set of motion, it's moving with steady acceleration. That's what we're saying. That I'm not saying acceleration is going to be constant across the board, especially for horizontal problems. For vertical problems, it's a little different. But we don't mean that acceleration is always going to be 2 or, whatever. But within that particular problem, you have constant acceleration. Okay? And then what would T be? Yeah, good. Time is in seconds. Okay, so V equals V sub O plus AT. Questions on that one? Okay. Here's our next equation. All right, so let's walk through our variables here. X, what do we think that probably means? Displacement or final position. Okay, and it's final because it's by itself. So you can put final displacement. And we know that since it's x, it's going to be horizontal or vertical? Horizontal. Okay, we haven't gotten to vertical problems yet, but when we start dealing vertical, your book will start calling this a y instead. Okay, but final displacement would be in meters. That means x sub o would be initial displacement or initial position. Also in meters. We know what v sub o is, we know what t, we know what acceleration is, or a, and we know what t is again. Okay? So this is about plug and chug once you find these variables and start identifying them. Remember that we have to become really good at identifying variables based on their units. That's why I'm kind of putting such an emphasis on their units. Okay, we've got to be able to pick things out of a word problem based on units if you can't tell otherwise. Okay? Here's our third one. V squared equals v sub o squared plus 2a x minus x initial. Sometimes you'll see that last term written as a delta x. It means the same thing, final x minus initial, or final position minus initial position. It means the same thing. And here's our last and least used equation. Okay, those first three that we gave you, you will use all the time. And it would be very good for you to start memorizing those or committing those to memory just for convenience sake. But this is our last equation, and all this means is average velocity. If we were looking at two different things, we wanted to find our average velocity. That's what the bar over top of the variable means is average. Okay, so if you ever see a bar over that letter, it just means average. So to take the average of something, add them together, divide by how many you have, right? So we're adding final plus initial, we're dividing it by 2. Okay, we rarely use this equation, but I'm going to give it to you anyway. Okay, so we've got our 4 equations. I would box those, star those, make sure that you know what page those are on. Those are equations you will use day in and day out in this class. Literally, until the end of the year, you will use those equations. Okay, so those are ones you will probably end up knowing, but I think it's nice for you to have. Okay, so first and foremost, please read the whole problem. Okay, please, please, please don't assume you think you know what it's going to ask and then start working. Okay, so many times people will start a problem and then they realize they're completely solving for the wrong thing. Okay, or they didn't read that the question was asking a very simple question or things like that. Just take the extra 4 seconds, read the whole problem, okay? Don't assume you know what they're going to ask. Draw a diagram if it's necessary. Right now, we're not really at a place we need to start drawing a bunch of diagrams. When we get to projectiles, we'll start drawing a lot of diagrams, things like that. So right now, we're not really there yet, but I think it maybe is a good habit to get started, okay? Write what you know and determine what's to be found. Have we talked about making a list in your margins of your variables? Okay, a little bit or no? Yeah. Okay, I like to list everything that I have in the margins. So as I'm working through a problem and I see initial velocity, I'll write v sub o equals blah, blah, blah. If I have a time, it equals this. If I know I'm solving for acceleration, I like to put a question mark because I know what I'm solving for. Okay? Having these variables on the side will help you narrow down which of those kinematics equations to use. Because if you take a look at those equations, some of them don't even have particular variables in them. One of them doesn't have final velocity in the equation at all. So if they don't give you final velocity and you're not solving for it, that might be a good clue that that's the equation you have to use. Does that make sense? Narrow down those things by the variables you're given. Okay, consider what equation you should use, calculate, and check your answer. Does it make sense? Does it have correct units? Those are two things we always have to check for. Okay. Now, granted, high school physics problems might not always make perfect sense, but, you know, Just go with it. Okay. But we do want to make sure that it's at least reasonable. Okay. And check for correct units. Okay, let's start identifying our variables here. We're going to hang on to this number for just a second, this 27.8. What this is telling us is that it needs to reach this certain final velocity. But our question is asking us, can the airplane reach the proper speed? Okay, so this 27.8 is a reference number for us. This is not the plane's final velocity. Okay, this is a reference number. We're going to solve for final velocity and see if it meets this standard, what it needs to be. Does that part make sense? Okay. So let's go ahead and start identifying what we do have. We do have its acceleration. We do have its initial velocity, don't we? Zero, yeah, it's zero. Right? We're talking about a plane starting on the runway, speeding up to try and take off, right? Does that make sense? We can picture what's going on here? Okay. And what else do we know with this number? It's our x. What about our x initial? Zero. Good. Our initial position is the starting point of the motion at which we just consider that our origin, right? That's where we're starting the whole thing from. Okay, so let's take a look at our kinematics. We need to solve for velocity. We need to solve for final velocity. What major factor are we missing here? Time. Is there one of those equations we can solve for without having time? Yeah, our third one, right? V squared equals V sub O squared plus 2A delta X. So we're going to say V squared equals V sub O squared plus 2A X minus X sub O. Okay, we're solving for V squared, so that's going to stay put. V sub O squared is just 0. 2 times 2 times 150. Combining this term right here, we should have 600. So how do we get V by itself here? What did you say? Square root both sides. Very good. So we'll square root the V, square root 600, which would give us V equals, I got 24.5, yeah? Okay, so that's the final speed that it will reach by the time it needs to take off. Is it going to make it? No, it's not going to make it. It did not reach this speed that it needs to have by the time it takes off, so it's not going to do it. Okay? Does that make sense? Okay, so that's something that we've got to pay attention to when we're reading our problems, because how many of you initially wanted to plug in 27.8 as final velocity? Right? I think initially reading the problem, almost anyone would. That's tough to see. Okay? Very good questions there. Does the math easy, right? Once you plug them in, the math part is actually pretty simple. Okay? What do we know? What are we solving for? What equation we use? We already did all that. Okay, so now we're going to do a continuation of that problem. What length does the runway need to be in order for the plane to have a successful takeoff? Okay, if we want a successful takeoff here. So what length does the runway need to be? If we want to reach that speed and we want to have a complete takeoff, That means we're solving for x this time. Okay, because we want to find out what length of the runway. What does that mean this time our final velocity will be? 27.8, very good. Our initial velocity would still be 0. Our initial position would still remain 0. And our acceleration would remain the same at 2.00 meters per second squared. We still don't have time, right? They didn't give us time yet. So we can still use that same equation. V squared equals V sub O squared plus 2a x minus x sub O, right? Okay, and since this is x minus 0, we don't need to include that 0 really. Since our initial position is 0, we can leave that out. Okay? So what I'm going to do is I'm going to go ahead and take 27.8 squared. That gives me 772.84 equals 4x. Everyone okay with that term, right? This step to this step? Give me like a head nod if we're good with that. Okay. From there, all we do to solve for x is divide by 4. Divide by 4, which means our final displacement needs to be, I got 193.21 meters. Yeah? Okay. So that means we were about 40-some meters short, 43 meters short on our original try. Okay, go ahead and get this one written down, or get written down what you want to or need to, and we'll start working through it in just a second. All right, let's go ahead and start identifying our variables here. Oops. All right, we know t, 5.21. We know distance, so that would give us which variable specifically? Just x. X sub O would be 0, okay? Almost every single problem that we do, x sub O is going to be 0, so you can continue to write it, you can leave it out. That's up to you, just as long as you understand that that's got to be a variable that you plug in. Okay. We want to find acceleration, so that's our question mark. And what else do we know? We know one other thing. Initial velocity. We know V sub O is 0. Very good. Very good. Okay. What equation can we use? Because we're missing final velocity. So which equation can we use? The second one, right? X equals x sub O plus V sub O t plus 1/2 AT squared. All right, so now we just plug and chug, okay? Plug in our variables and get our answer out. This right here is a very, very important thing for you to notice. Here, only the t is squared, okay? This whole entire term is not squared. It's only time, okay? So only 5.21 is squared. Acceleration is not, 1/2 is not, okay? Just the t. Just the t. Okay, so please do not square the whole term. Okay, so if I combine these two terms right here, I get 13.57a. Does that look right? Okay, good. And then we divide over 110 divided by that, and it means our acceleration is about 8.10. Okay, so our first question here, our first goal is to find acceleration. You can find acceleration using two different equations here. Okay, our very basic equation, A equals delta V over delta T, or you can use our first kinematic equation, VF equals VO plus AT. Okay, and I just want to show you that those two equations are literally the same thing. Okay, velocity final minus velocity initial over T. That's the same as delta V over delta T. If I move T to the other side, that means I'm left with T times A equals V minus V sub O. If I add this over, that means I'm left with V equals V sub O plus A times T. That's our exact first kinematic equation. So those two equations are exactly the same. They work the same all the time. So you can use either one. Okay, so here we know our initial velocity is 18.5. We know our final velocity is 46.1. We know our time, 2.47. Okay, so I will go ahead and plug it into our kinematics equation. 46.1 equals 18.5 plus acceleration times time. First thing we should do here is subtract the 18.5 over. That gets subtracted over first, and then we would divide by our 2.47. Do we have an acceleration value? 11.17. Do we agree with that? All right, very good. Our next goal is going to be to find distance traveled, okay, or x. Which equation should we use probably to solve for that? We could really use any of our any of those last two, right? But which would be simpler? The second one, because it's literally setting x equal to the rest of the problem, okay? It just makes it a little simpler solving it and having to do less rearranging, but you can do it with either of those two equations. Okay, so we're solving for x here. X sub 0, okay, or initial position would still be 0. Here we have an initial velocity, so we've got to plug that in times our time. And remember, only the time variable is squared. Okay, that means our final distance or total distance traveled is what? What'd you get, Vivian? What do you think? Like that? Is that what you said?
No, just 79.77.
Not the 179. Is that what everyone else got? Okay. 79.77 meters.